So taking a look at this first problem, we want to be able to figure out where are the absolute maximums. There's a typo there. It's supposed to be maximums. The absolute minimums, the local maximums, and the local minimums. So that's going to be one of the big themes as we go forward here is those maxima and minima, both absolute and local. So let's start with absolute. What is the absolute maximum for this graph? At what letters does that occur? Yeah, B and F. Because you'll notice both of those are as high as it goes. Now notice we are allowed to have two absolute maximums like that. All right, what about absolute minimums?
E.
Yep, that's at E, because the lowest it ever reaches is E. Now what about local maximums and local minimums? So like, what's a local maximum? D. Is F a local maximum? It was an absolute maximum, so just on that basis we could say no.
Would B go?
No.
What about B? Is that a local maximum? Well, that was also an absolute maximum, so we could rule it out for that reason. So just the D there. What about local minimums, though? This is where things get interesting. So for local minimums, one of them is C, because you can see the graph is kind of bottoming out in that area. The question, though, is A a local minimum?
No.
And actually the answer is no.
Oh, because
It's not even an absolute minimum. Oh,
So a local maximum or minimum must be the max or min from both sides. Now notice
E is
F.
absolute.
Leon, shush.
F cannot be a local maximum or minimum, and nor can A be a local max or min, but they can still be absolute. So you'll notice A is nothing, because that's not the absolute minimum, but F is still an absolute maximum. That's still okay. So when we talk maximums and minimums, absolute can be at endpoints, local cannot. All right, so taking a look at each of these, we want to figure out what are the locations of the absolute and local maxima and minima. So take a moment, look through it and process it through, then we'll talk it through together here in a moment. All right, so I'm just going to go through them kind of in order here. So let's start with A. Is A anything?
Yes.
Yes, it is. Now, because A is an endpoint, we know it's not local. So the only thing left then is that it could be an absolute max. Absolute max or min. In this case, it's an absolute min, because that's as low as it goes. Notice if I go along here, it never goes any lower than that. So that is the absolute minimum value. All right, next up, B. B is the local maximum. C. Is C anything?
Yes.
Yes. We actually can deal with C. That one's going to be a local min.
Yep.
D. What is D? Yeah. It's a maximum, but notice it's actually the absolute maximum because it's the highest that the graph ever reaches. Not just local, but absolute. And what about E?
Nothing.
E,
Oh, wait.
it is a local min. Now notice nothing is given for this point here. No letters associated with it because it is nothing. There is nothing special about that point there. Just being at an endpoint that's not an absolute max or min. Now as we take a look at this, notice like there's multiple local mins. That can totally happen. Now how do we know? Basically what you're doing is you're looking over a certain region. So like if I look between here and here, C is the minimum within that range. Same kind of thing happens between these two. Basically, near that point, that is the minimum. It's more than that on both sides. And in fact, we can even define these and put them into notes here. And you can see here that for something to be a local minimum, our y value must be lower than all other y values from both sides of that x at c. Now there's a lot of details in here, a lot of notation. Take a moment, write this into your notes. We're going to use those definitions to figure out where are the absolute and local maxima and minima for this particular graph. And again, I'm just going to go through it just piece by piece here. So let's start here at -1. Is this point anything? Well, it's at an endpoint, so it can't be local. It has to be absolute. Is that the absolute maximum?
No.
No. Is it the absolute minimum?
No.
No. So that one's nothing then. Okay. What about here? Is this point anything at 0 here? Well, it's an endpoint again, so again it can't be local. Is it the absolute minimum?
No.
Nope, and certainly not the absolute maximum, so no, that's nothing as well. What about this point?
Wait, no, it's not, because it's an open circle.
Oh, now things get tricky, huh?
Wait.
Because,
Wait, can it be because it's like right
remember in our definition, we'd be saying like f of c. Well, in this case, c is 0. F of 0 here is actually this number. It's actually going to be 3. This is an open circle, and that fact that that's an open circle throws everything off. That is actually nothing there. It is not an absolute maximum because we can't say it's approaching 5 up here as the maximum because it actually has to be a number of where the maximum is. And since it doesn't reach 5, it's not 5. All right, next candidate is this stuff right here. Is that anything? Well, really our point is right here. That point. As I go to the left, all the points, notice, are higher than it because we're up here. Okay, as we go to the right, notice all the points are higher than that. So, it actually is something. This is a local minimum. Now notice though, the local minimum is where the actual point is in this case. It is not up here where the open circle is. So my local minimum here is 2. Specifically the coordinates 2, 2. Right, next one. Did you notice this one? That is a local max. So we got a local maximum there because it's peaking out at that point. What about here? Is that anything? All the way out here at x equals 4. Is that point anything? Yes. It looks like a minimum. Is it an absolute or a local minimum? Nothing ever gets lower, so yes, it is absolute. Okay, going from there. Notice we have another point here that we have to consider. That is something. That is a local max. And finally, this point here, what is that? Nothing. Absolutely nothing, because it's an endpoint, so it can't be local, but it's also not as low as it goes because the absolute was down here at 1, and so it's nothing. All right, now there's actually some little detail-y stuff that we have to dig into related to this kind of thing. So, need you to really process through this information, so make sure you're really thinking about what this means as we read through it. Consider some function f over the interval a to b. Notice that it includes points a and b, so it's a closed interval. Let f of c, so that's the y value, be the absolute maximum, and f of d be the absolute minimum. What has to be true about function f in order for us to know that f of c and f of d exist? That is, what must be true about f in order to know that the absolute maximum and the absolute minimum are actually going to exist somewhere on this interval? Okay. So let's look at an example here. In this function, We have f, and we have some interval of the graph shown. Does a absolute maximum exist? Kind of hard to tell on this one because it might be here, but it might not be because this might be continuing up forever. So maybe, but maybe not. But in this case, this could be the absolute maximum if it were higher. What about the absolute minimum? Well, that gets tricky because notice it's approaching an asymptote. As we approach the asymptote, my graph is approaching negative infinity. That won't work. We can't say that we have an absolute maximum or minimum at infinity or negative infinity. It has to actually be a number for a max or a min. Okay, so this one would not qualify. Notice what's different about this graph than maybe some other graphs here. And let's look at one more example. Does this graph have an absolute maximum? Well, that'd be like this point here, but that's an open circle, isn't it? So it doesn't have an absolute maximum. So this also would have to violate the rule allowing that to happen. Now it does have an absolute minimum. It has an absolute minimum, but it doesn't have an absolute maximum. So what do we know must be true? So here I have my two numbers. I just plotted the endpoints. Would this graph have an absolute maximum and minimum?
Yeah.
Yes, it does. Would this graph have an absolute maximum or minimum? Yeah. Okay. What about this graph? Does this have an absolute maximum or minimum? Yes, it does. It's the endpoints in this case. That is okay because we're on a set interval. Okay. How could I draw this graph? What would I have to do in this graph in order for me to make it so there wasn't an absolute maximum or minimum?
I'm gonna have to go through the place.
Well, remember the graph we saw earlier where we had this sort of thing going on? We had an asymptote there, right? So if there's an asymptote, that causes a problem. Okay, and the other one that we looked at, it did one of these. What's true about both of those graphs? So if it's not continuous, then it doesn't necessarily have a maximum or minimum. But if f is continuous on a closed interval, notice the interval has to be closed because otherwise we'd have open dots at the ends and then it might not. Then we actually do achieve an absolute maximum and an absolute minimum at some point. This is called the extreme value theorem, and yes, this should go into your notes. You will see questions come up where it asks you, does this meet the extreme value theorem? What does it fail in when it comes to extreme value theorem? Things like that. So make sure you have this in your notes and all its little annoying details. All right, so you got extreme value theorem into your notes now. Each of these three graphs down below are just examples of the extreme value theorem actually taking place. So this first example, this one's an instance where you just have an absolute maximum and an absolute minimum happening in the middle there, because it can go ahead and achieve those points anywhere. But notice we also can have examples where one of those or both of them even can happen at the endpoints. That's why it has to be a closed interval, because for instance at the end here, if this was an open dot, well then it wouldn't actually be the absolute minimum. So we actually have to have it be a closed interval for that reason. And then the last graph here, notice it shows two instances where we hit the absolute maximum, and that's okay too. This theorem doesn't say it's going to happen exactly once. It just says that it will happen, sometimes more than once. Now continue with some of these ideas here. You've seen this graph earlier, but earlier I asked a different question. This time, what is the derivative at each of these maximums and minimums, please? So take a moment, look over the graph, and figure out what is the derivative at the local maximums and the local minimums. All right, so we're looking just at local maxima and minima. So A, remember, was not a local minimum, so I'm not going to worry about that. What about at B? What's the derivative at point B here? Well, remember, derivative is slope of the function, right? Slope of the tangent line. What's that slope? 0. So my slope here is 0. What's the slope at point C? Now this is where things get tricky, right? As you've been seeing already in the assignment you've been working on today, there are points where it's not differentiable. One example about a place where it's not differentiable is at a corner in our graph. So in fact, in this case, my derivative does not exist. Okay, what about point D? What's our derivative there? Yep, derivative is 0. Okay, what about E?
0.
Yep, the derivative is 0. And so you'll notice that all of these local maxima and minima were happening where the derivative was one of two things. It was either 0 or the derivative didn't exist. Those particular points actually fall under a bigger umbrella. These are all examples of critical numbers. And so again, a piece for your notes here. Our definition of what a critical number is, and then a little bit of information about the critical numbers down here. So put this into your notes, and then we'll see how to use it as well a little bit. All right, so we can see the definition of what a critical number is. Basically, it's anywhere where the derivative is 0 or the derivative doesn't exist. Those are all of our critical numbers. Now, you'll notice here there's some additional information. If f has a local maximum or minimum at c, then c then is automatically known to be a critical number of f. A question though related to that. Will every critical number also be a maximum or a minimum? Can we say that? Well, critical numbers are places where the derivative equals 0. Okay, those are generally going to be maxes and mins, yes. Or where the derivative doesn't exist. Remember how a graph can be not differentiable at a point. So each of these three graphs represent ways that the graph is not differentiable. In this case, it could be a corner. Now in the case of a corner here, that is a critical point. And actually they're all critical points, but rather it is a maximum. But what about a discontinuity like this, either a jump, a hole, or an asymptote? Notice this particular graph does not have a maximum. And so it's not always going to be a maximum or a minimum just because we know it's a critical number. It works one direction but not the other. And also vertical tangents is the other way that can happen. So one last way to practice this. Please take a look at this graph again. And this time, what is the derivative going to be at each of the critical numbers? So you need to know what's a critical number, and then what's the derivative at that number. So when we go to find these derivatives now at the critical numbers, first thing we need to know is where the critical numbers are. As you looked over this, hopefully you identified, actually I'll mark them down here on the axis, critical numbers at -1, 0, 2, 3, 4, 6, and 7. So all of those are critical numbers. What is the derivative at -1?
Either 0 or D and E.
Well, the derivative, remember, has to exist from both sides. So
D and E.
does not exist. What's the derivative at 0?
D and E.
D and E.
The net.
What is the derivative at 2?
The net.
Does not exist. What is the derivative at 3?
0. 0.
Yep, at 1, 0. What about at 4?
The net.
Does not exist. It's a corner. What about at, I lost count here, 2, 3, 6.
0.
Yep, at 6 it's 0, and at 7 it is
The net.
the NE. Yep, because it's an endpoint.